This section introduces the address resolution protocol and its role as part of network layer operations. So in order for data transmission to a network destination to be achieved, it is necessary to build association between the network layer and lower layer protocols. The means by which the address resolution protocol is used to build this association and prevent the unnecessary generation of additional broadcast traffic in the network should be clearly understood. So upon completion of this section, it is generally expected that trainees will be able to explain how the MAC address is resolved using ARP and explain the function of the ARP cache table. The Address Resolution Protocol, or ARP, is another protocol that, like ICMP, has a close relationship to IP. While IP provides the logical path between a source and destination, which may or may not exist within the same network segment, the actual transmission of data relies greatly on the lower layer protocols, such as Ethernet, in order to support the physical transmission. The problem faced during encapsulation is that IP is but one of many protocols that can be used over Ethernet, and therefore Ethernet requires a standardized means of communication over the physical Ethernet medium, which is achieved through MAC addressing. IP is capable of defining the IP destination, but to actually reach that destination, Ethernet must provide the next hop as a physical destination address on the local segment in the form of the destination MAC address. We can use the shown example to demonstrate this issue. Host A is part of the 10.1.1.0 network and therefore belongs to the same network as host B. Therefore, we can consider that both hosts are on the same physical segment. Packets destined for host B from host A will be forwarded based on the IP address of host B. Applications that generate data will typically specify the destination IP address. Host A is able to identify at the network layer through IP that the address for host B is part of the same network, and therefore the network of host B is known by host A. However, before host A is able to perform encapsulation, the sender must be able to identify the destination MAC address of host B in order to reach the destination over the physical medium. If this step were not performed, communication would only be possible through broadcast transmissions at the data link layer, which would cause unnecessary interruptions to end stations within the same network segment. If host B happened to exist within a different network, host A would be required to discover the next physical hop, which would be the interface of the IP gateway. We show here the general frame information that host A will possess, along with the information that is unknown, which basically is the destination MAC address. It should be noted, however, that the encapsulation will not be performed until this information is acquired by the sender on the physical segment, which is basically where the address resolution protocol comes in. As part of the TCP/IP protocol suite, ARP is considered to be a network layer protocol with a primary objective of allowing the logical path defined by IP to have association with a physical path over the local segment, meaning that the operation of ARP has a strong reliance on Ethernet. ARP packets are generated and encapsulated within an Ethernet 2 frame header to allow the ARP packet to be forwarded over the physical segment. We demonstrate here the format of the ARP header and the various fields that are required in support of the address resolution process, which refers to the association of a destination MAC address with a given IP destination. The hardware type refers to Ethernet as the physical network standard and the protocol type being IP. The hardware length and protocol length defines the address lengths in bytes for both the Ethernet MAC address and the IP address, respectively. The operation code plays an important role in determining whether an ARP packet is being sent as a request or being returned as a reply. This will also determine how the receiving end station reacts to the ARP packet. If the packet being received is a request, it means that the receiver is expected to generate a reply packet. If the received packet is a reply packet, the packet will be processed and discarded. The operation code is a 16-bit field that is capable of supporting up to 65,536 different operation codes. However, the vast majority of these operation codes are either reserved or unused. In this instance, however, only 2 operation codes for ARP requests and ARP replies are required to be understood. The protocol address refers to the IP addresses from the perspective of the sender, whilst the hardware addresses refer to the MAC addresses. Since the sender is unaware of the destination MAC address to which to forward data currently, the destination hardware address field is not populated with a valid MAC address initially. Since there is no IP header, the range of ARP packet transmissions is restricted to the boundaries of the local network, and such is unable to traverse IP gateways. We represent here a typical scenario in which ARP is required. The example involves 3 hosts in the form of host A, B, and C. We can understand that all 3 hosts are part of the same network, and each has a unique MAC address. The basic scenario involves host A wishing to successfully transmit data to the destination of host C. Host A is generally aware of the IP address of the end station to which it wishes to forward the data, which in this case is the IP address of host C or 10.0.0.3. However, before data can be forwarded to the intended destination, the physical path must be known. We should consider in this scenario that this represents the first time that host A is attempting to transmit data to host C. The first stage of any ARP process is to determine whether the ARP process is actually necessary at all. Any device that operates at the network layer will contain what is known as an ARP cache table that is used to record the IP address and the MAC address to which it is resolved. The end station must determine whether such an association currently exists and has been recorded in the ARP cache table. If the IP address and MAC address has been previously resolved and it is discovered in the ARP cache table, a hit is considered to have been achieved and the address resolution by ARP is not required. In this instance, however, we can clearly see that the ARP cache table is empty and therefore no hit can be achieved, meaning that the ARP operation is required. The ARP or ARP request process involves the generation of an ARP packet that is populated with information that is known to the sender, which in this case is host A. Host A will include its own MAC address and IP address within the source hardware and source protocol fields respectively, as well as the destination protocol address, which is the IP address of the destination, which in this case is host C. Host A is currently unaware of the hardware address of the destination for which the ARP packet is being generated, and therefore the destination hardware address field is initially populated with a hexadecimal string that is equal to 0. The operation code in this case is set to request, which indicates that a reply is required from the receiver. Once the ARP header has been populated, it is encapsulated inside an Ethernet 2 frame header that is again populated with the source MAC address of host A. Since the destination MAC address is unknown, the frame must be transmitted as a broadcast frame, and therefore the destination MAC is populated with the MAC broadcast address that is represented as an FF hexadecimal string. One final point to note is that while the addressing in the frame header is used for frame forwarding, the addressing in the ARP header is used solely for the population of the ARP cache table. As the frame is broadcast over the physical medium, an instance of the frame shall be received by all hosts, with the exception of the sender, causing some level of interrupt to other end stations on the network, which is an unnecessary evil of each ARP request. However, with regards to the bigger picture, the ARP process helps to reduce such broadcasts and interrupts to other end stations. Host B will ultimately ignore the ARP packet following the frame processing. However, in the case of host C, the end station will utilize the information within the ARP header in order to populate its own ARP cache with information that allows the MAC address of host A to be resolved. As a result of the ARP request packet from host A, host C is able to populate its own ARP cache table with information that allows host C to know how traffic destined for host A from host C should be forwarded, and the Ethernet MAC address that host C should use as the destination address for this traffic. We should also notice that the entry in the ARP cache table is considered dynamic. This means that the entry was determined through ARP. It is also possible for static entries in the ARP cache table to be manually configured, which reduces the need for ARP, but in the event that the IP address of the host is changed, the ARP cache entry would become invalid, and removal or renewal of the entry would require manual intervention from an administrator. As a result of the ARP cache entry, traffic destined for host A can now be forwarded directly to the intended destination as a unicast transmission, as opposed to a broadcast, which ultimately reduces traffic flow within the local segment and unnecessary interrupts to other hosts. In response to the original request from host A, host C is now expected to generate an ARP reply that will be used to inform host A of the MAC address that should be used to reach host C, and allow host A to create a binding within its own ARP cache. Host C starts by generating a new ARP packet and populates this packet with the information it possesses in the same manner as we saw being performed initially by host A. In this case, however, host C is the source and host A is the destination. Since host C is aware of its own MAC address and also the MAC address of host A, it is able to populate all fields within the ARP header. The source MAC address represents the information required by host A, and the operation code in this instance is set to reply, to indicate that the packet does not require a response from the receiver. The packet is encapsulated within a frame header. However, this time host C is able to use the information within its ARP cache to determine that any packets destined for 10.0.0.1 or host A should be forwarded to the MAC address of 0001020304AA, effectively enabling a unicast transmission to be performed. The ARP reply, once received by host A, will be processed and the frame header discarded. The information in the ARP packet header will then be used to populate the ARP cache table of host A. It is important to note that the MAC address used to populate the ARP cache of host A is taken from the destination MAC field of the ARP packet and not from the destination MAC field of the Ethernet frame header. The resulting operation of ARP means that host A now has a forwarding path for all packets destined for the IP address of 10.0.0.3. The entry will remain in the ARP cache for a set period of time that varies depending on the ARP entry timer of the operating system being used. We should now be somewhat familiar with the common operation of ARP as a means of resolving MAC addresses to IP addresses. ARP, however, is also used to support a number of other processes, some of which are now redundant and some which are still in use. Proxy ARP represents one such example of a number of applications of ARP, and in order to understand the application of proxy ARP, the principles of IP addressing and subnets are required to be clearly understood. We should start off by realizing that host A and host B are technically part of the same logical network, since the addresses of 10.1.0.1/8 and 10.2.0.1/8 are considered part of the same 10.0.0.0/8 network. If the addresses are translated from the dotted decimal format into binary, we're able to clearly identify that the bits that represent the network address are identical. We notice, however, that the two hosts are not considered part of the same physical segment, and are in fact divided into two separate physical segments as a result of the gateway. If we follow the general principles of ARP, host A would determine that 10.2.0.1 is part of the same 10.0.0.0 network, and so discovery should be possible by generating an ARP request. The IP gateway, however, does not see this the same way, and would restrict the ARP request since broadcasts are not forwarded by gateways. Another point to consider is that the gateway is unable to associate two interfaces with the same network segment. We find that from the perspective of the gateway, interface gigabit Ethernet 000 is part of the 10.1.0.0/16 network, and interface gigabit Ethernet 0/0/1 is part of the 10.2.0.0/16 network. Any IP packet received from host A with the source IP address of 10.1.0.1 will be perceived by the gateway as being received on the same 10.1.0.0 segment as to which the gateway belongs. The reverse is true of host A, who would assume that any packet originating from the gateway with the source IP of 10.1.0.2 originated on the same 10.0.0.0 network to which host A belongs. The problem remains then, how can we allow hosts that belong to the same logical network but separated by a gateway to operate as if they were part of the same physical segment? The solution to this is to change the behavior of the IP gateway to act as a proxy device for ARP requests and replies. We should assume that an ARP request is generated by host A intended for 10.2.0.1. The ARP request is broadcast over Ethernet and ultimately received by the gigabit Ethernet 000 interface of the IP gateway. Instead of discarding the broadcast frame, the gateway will update its own ARP cache and generate a new ARP request destined for 10.2.0.1 that will be broadcast via the gigabit Ethernet 001 interface. The request will reference the MAC address of the interface of gigabit Ethernet 001 to which the receiver with the destination of 10.2.0.1 should reply. Host B, upon receiving this request, will update its ARP cache and generate a reply destined for the IP address of host A, but the MAC address of the gateway's G001 interface. Once the gateway receives this ARP reply, the gateway will process the information and update its ARP cache with the details of host B, before generating a new ARP reply, again using the MAC address of its own Gigabit Ethernet 000 interface as the source address, before forwarding the ARP reply to host A. Upon receiving the reply, host A will update its ARP cache to resolve the IP address of host B unknowingly to the MAC address of the gateway's Gigabit Ethernet 000 interface. As a result, all traffic destined for host B will now be forwarded over Ethernet using the MAC address of the Gigabit Ethernet 000 interface of the IP gateway that will bridge the communication between the two segments. Proxy ARP is ideal for allowing a larger number of hosts that are part of the same logical network to be supported as if they were part of the same physical network, whilst allowing the gateway to act as an intermediary between segments and reduce the general levels of traffic generated in each segment. Another common use of the address resolution protocol is as a means of detecting duplicate addresses within the network. Gratuitous ARP is initiated at the point at which a new IP-enabled host is added to the existing IP network, or in the event that the existing IP address of the host is changed. In order to distinguish the host from all other hosts within the same network, the host is expected to have a unique IP address. ARP ensures this by generating an automated ARP request that includes the IP address of the source and issues this address as the destination IP address in the ARP packet. We can see from this example that host A has an IP address of 10.0.0.1 and that this IP address has in fact been assigned as the destination IP within the ARP packet. In doing so, the ARP request will effectively request that any host that has the same IP address as host A generate an ARP reply to be returned to the reference source MAC address in the ARP packet. If no reply is received to the request, host A can safely consider that the IP address of 10.0.0.1 is unique within the network. If a reply is returned, however, a notification will be generated informing that a conflict of IP addresses has occurred within the network, for which it is expected that a unique address be assigned. In summary for this address resolution protocol section, then we ask two questions here. The first is, prior to generating an ARP request, what action must be taken by an end station? Well, a host must determine whether it is aware of the physical path to which traffic should be forwarded before resorting to generating ARP requests. The host will do this by consulting the ARP cache for a valid address resolution between the intended IP destination in the local segment, or the IP gateway, which represents the next hop to the ultimate destination, and the destination MAC address that should be used as part of the frame encapsulation. When are gratuitous ARP messages generated and propagated on the local network? Well, a gratuitous ARP packet is generated and propagated over the local network in the event that either an IP-configured device is connected to the network, or when an existing device on the network is assigned an IP address or the existing IP address is changed.